You looked at the night sky last night or last year, or at some point you still remember, and you saw stars. That is not what you saw. What you saw was light. Specifically, old light. Light that left its source anywhere from 4 years ago to several thousand years ago, depending on which point of brightness your eye landed on. The stars that produced that light, in most cases, are no longer in the state they were in when the light began traveling. Some of them are not in any state at all. This is not a reframing. This is the physical description of what happens when a human eye receives photons from the night sky. You are not seeing objects. You are seeing signals from the past arriving now, carrying information about conditions that may have ended before your civilization began. The question that follows from this is not how far away they are. That question has been answered. The question is what it means to look at something that might not be there and have no mechanism for knowing. That is where things get genuinely hard. And I want to go there precisely. Light travels at roughly 300,000 kilometers per second. That number is so large, it becomes abstract within a second of hearing it, so here is a reference point that keeps it grounded. At that speed, light crosses the distance from Earth to the Moon in about 1 1/3 seconds. Earth to the Sun, 8 minutes and 20 seconds. The nearest star system beyond our own, a triple system roughly 4 light years from here, takes 4 years and 3 months for its light to reach us. When you look at that system's brightest component, the one Ptolemy cataloged in the 2nd century and named after the centaur, you are seeing light that left more than 4 years ago. Not approximately 4 years. Exactly. What you see is the star as it was 4 years ago. Whatever it is doing right now, in the physical present of this moment, is invisible to you. That information has not arrived. Now, look at Betelgeuse, Orion's right shoulder, one of the most recognizable stars in the northern winter sky. A red supergiant, a star so large that if you placed it where our sun is, its outer atmosphere would extend past the orbit of Jupiter. Betelgeuse sits roughly 700 light-years away. When you look at it, you are seeing light that left the star around the early 1300s, in the same era when the Mongol Empire was at its height, when the Black Death had not yet reached Europe, when no human being alive had any concept of what a light year was or what the word light year might mean. Whatever Betelgeuse is doing right now, you will not find out for 700 years. This matters more than it sounds, because Betelgeuse is not a stable star. It is a red supergiant in the late phase of its life, and astronomers have been debating for decades whether it is approaching the end. In 2019, it dimmed significantly. The brightness dropped to roughly 40% of its normal output over the course of several months. This became known among astronomers as the Great Dimming. The question was asked in earnest, is this star beginning to die? The answer, after months of analysis by teams at the University of Washington and elsewhere, was probably not yet. Probably a cloud of ejected dust obscuring the photosphere, combined with convective motion in the stellar surface. Probably. The word probably carries weight here. So does yet. Because here is the physical reality. It is entirely possible, not as a thought experiment, as a statement about what is actually happening in space right now, that Betelgeuse went supernova last century, or 50 years ago, or last decade. The light from that explosion has not reached us. We are looking at a star that may have already ended, in the form we observe, and the news of its death is currently crossing interstellar space and will arrive sometime in the next several hundred years. Or it won't arrive for 1,000 years. Or 5,000. We do not know when Betelgeuse will go. We know it will. That's the extent of it. What you see when you look at Betelgeuse is not Betelgeuse. It is a message that Betelgeuse sent 700 years ago, informing you of its condition at the time of transmission. Now extend this outward, because the travel time problem is only the first layer. The second layer is stellar mortality at scale. On a clear night, away from city light, the naked human eye can resolve roughly 5 to 10,000 individual stars, depending on latitude and atmospheric conditions. That number varies, but call it 8,000 as a working figure. Every one of those stars is in a different phase of its life cycle. Some are young, a few million years old, which in stellar terms is early infancy. Some are middle-aged, some are old. Some are, by any astrophysical definition, in the process of dying. The lifespan of a star depends almost entirely on its mass. Small red dwarf stars, the most common type in the galaxy, burn so slowly and so efficiently that the oldest ones have barely aged since the beginning of the universe. The universe is not old enough for a red dwarf to have died of natural causes. None has, not one. Meanwhile, the most massive blue stars, the ones burning tens of thousands of times more luminous than the sun, exhaust themselves in a few million years and explode. A few million years is nothing. The dinosaurs lasted longer than many blue stars. This means that of the stars visible to the naked eye tonight, some fraction, the massive ones, the ones burning fastest, the brightest ones by intrinsic luminosity, have already ended. Not tonight, not in any time frame that touches a human life. But in the astronomical sense, between the time their light left them and the time it reached your eye, some of those stars crossed the boundary. William Herschel grasped a version of this in 1785. He was working at his observatory in Slough, England, conducting a systematic survey he called Gauging the Heavens, pointing his telescope at hundreds of different regions of sky, counting the number of stars visible in each field of view, and using those counts to infer the three-dimensional shape of the stellar distribution. He was the first person to attempt a map of the Milky Way based on observation rather than speculation. The map was wrong in several important ways. He placed the sun near the center, which it is not, but the method was sound, and the attempt was unlike anything that had come before it. What Herschel also understood, intuitively if not mathematically, was that his map was not a map of the present. Every star in his count was seen at a different remove in time. The nearby stars were seen as they were a few years ago. The faint ones, at the edges of his survey, were seen as they were thousands of years ago. His map was a composite, a single image built from thousands of signals of different ages, all arriving simultaneously and being processed as if they described one moment. He called the structure of stars a stratum. The word he was actually groping toward was something more like a temporal archive that appears deceptively to be a spatial one. That is what the night sky is. A temporal archive, a stack of different pasts all arriving at once, appearing to the eye as a single present. The third layer is harder. And this is where I need to be direct with you about something that took me a long time to sit with comfortably. There is a boundary in cosmology called the particle horizon. It marks the edge of the observable universe, the sphere of space from which light has had time to reach us since the universe began. That sphere extends roughly 46 billion light-years in every direction, not 13.8 billion. The universe is 13.8 billion years old, but the horizon is larger than that because space itself has been expanding while the light was traveling. The sources that emitted the oldest light we can detect have since moved much farther from us. The expansion carries them away faster than we can intuitively account for. Beyond the particle horizon, we cannot see. Not because there is nothing there. Current models suggest the universe extends far beyond the observable bubble, possibly for an immense distance, possibly without limit. Though without limit is a phrase that physics treats with particular care. What exists beyond the horizon is unknown in the strictest sense, not unknown but inferable. Unknown because no information from that region has reached us, and given the geometry of the expansion, some of it never will. This boundary is not a wall. There is no wall. It is an information boundary, a surface in space-time beyond which signals have not had time to arrive. And because the universe continues to expand, because the space between us and distant objects continues to grow, the horizon itself is not fixed. Objects that are currently inside the observable universe, ones we can see, ones we have cataloged, will, over very long timescales, eventually recede beyond the horizon. The space between us and them will grow faster than light can cross it. They will disappear from view not because they moved, but because the space between us expanded them out of reach. Edwin Hubble established the expansion in 1929. He was working at the Mount Wilson Observatory in California, a site chosen for its dark skies and elevation 2,000 feet above Los Angeles, accessible by a road that had been built partly for the telescope's equipment. Hubble had been measuring the spectra of galaxies for years, and what he found when he plotted the data was that virtually all of them showed a redshift. Their light was systematically stretched toward the longer, redder wavelengths, as if the source was moving away. And the farther the galaxy, the larger the redshift. The relationship was linear. He established this using a distance measurement technique he had refined with Henrietta Swan Leavitt's work on Cepheid variable stars, stars whose intrinsic brightness pulses at a rate that correlates precisely with their true luminosity. Measure the pulsation period, calculate the true brightness. Compare with the apparent brightness as seen from Earth. The difference gives you the distance. Leavitt discovered this relationship in 1912, working at the Harvard College Observatory as a computer, a title given to the women hired to analyze photographic plates, work that was paid less than unskilled labor. She identified thousands of Cepheids in the Magellanic Clouds. Her discovery made Hubble's work possible. Hubble acknowledged the technique and rarely acknowledged her by name. What Hubble's data showed was that the universe is not static. Everything is moving apart, not because galaxies are flying through space away from a central point, but because space itself is growing between them. There is no center. There is no outside. Every galaxy is receding from every other galaxy simultaneously in all directions because the medium they sit in is expanding. This was not predicted. Albert Einstein had introduced a term into his field equations specifically to prevent this result, the cosmological constant, an ad hoc addition that held the universe static by counteracting gravity. When Hubble's data came out, Einstein visited the Mount Wilson Observatory and looked at the photographic plates himself. He called the cosmological constant the greatest blunder of his career and removed it from his equations. Georges Lemaitre had gotten there first. The Belgian physicist and Catholic priest had independently derived the expansion from Einstein's own equations in 1927, 2 years before Hubble's observations confirmed it. He wrote to Einstein directly. Einstein's response was that while the mathematics was correct, the physics was abominable. Einstein was wrong. He eventually said so. What the expansion means for the night sky is this. The light from the most distant objects visible in any telescope is already ancient, already stretched, already redshifted into longer wavelengths by the expansion of the space it traveled through. As the universe continues to expand, that light will be stretched further. Sources will recede further. The horizon will shift. On timescales that make the current age of the universe look brief, trillions of years from now, in a universe so cold and expanded that the physics of today is barely relevant, the cosmic microwave background radiation will be stretched into wavelengths too long to detect. The evidence of the universe's origin will have expanded beyond any possible observer's horizon. Any civilization that exists then, if one does, will look out at a sky containing only their local galaxy, surrounded by apparent darkness, and may conclude rationally, from the evidence available to them, that the universe is static and solitary and eternal. They will be wrong, but they will have no way of knowing. That possibility, a future civilization reasoning correctly from incomplete evidence to a false conclusion, is something I find genuinely troubling in a way that goes past intellectual interest. Not because I worry about that civilization. They are hypothetical and distant beyond any meaningful reckoning. But because it establishes something about our own situation that most accounts of science leave out. We do not know what information we are missing. We know we are missing some. We know the horizon exists. We know that beyond it, things are happening about which we will receive no signal. But we cannot audit the contents of what we can't see. The cosmic microwave background, the faint thermal glow left over from the early universe, the oldest light we can detect, emitted roughly 380,000 years after the universe began, when it had cooled enough for hydrogen atoms to form and photons to travel freely. That background was detected in 1965 by Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey. They were not looking for it. They were calibrating a microwave antenna that had been built to communicate with early satellites. The antenna picked up a persistent noise that would not go away. They checked for everything. They cleaned pigeon droppings from the antenna on the theory that biological contamination might be causing a signal. The noise remained. Robert Dickey at Princeton University, about 50 kilometers away, was at that moment actively searching for the background radiation. He had calculated that it should be there. When he heard about Penzias and Wilson's unidentifiable noise, he put the phone down and told his team, "Boys, we've been scooped." The noise was the oldest light in the universe. It had been traveling for 13.8 billion years. Penzias and Wilson were measuring an echo, not a star, not a galaxy, not any object, but a residual thermal glow from a state of the universe that no longer exists in any part of the observable cosmos. That glow is uniform across the sky to 1 part in 100,000. Everywhere you look, in every direction, the early universe left the same signal. The variations in that 1 part in 100,000 are where the seeds of every galaxy, every star, every planet, and every living thing came from. The map of those tiny variations is the closest thing we have to a photograph of the universe in its infancy. We can detect it now. This is not guaranteed. It is a feature of the specific moment in cosmic history in which we happen to exist. We arrived at the right time to read this. 3 things the physics does not tell us about what you see above you. 1. We do not know how many of the stars visible to the naked eye tonight have already gone supernova. We can calculate probabilities using stellar evolution models. We cannot point at any specific star and say that one is already gone. The light from the explosion is in transit. The number of stars in that category is non-zero. We cannot know which ones. 2. We do not know what exists beyond the cosmic horizon. The horizon is not the edge of the universe. It is the edge of the information we have access to. What lies beyond it, more space following the same physical laws, different physical laws, nothing at all, is outside the reach of observation. Models suggest it continues. Models are not observations. 3. We do not know what dark energy is. The discovery in 1998, made simultaneously and independently by 2 competing teams, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt and including Adam Rees, was that the expansion of the universe is accelerating, not simply continuing, getting faster. Both teams had been measuring the distances to Type 1a supernovae, a specific class of stellar explosion that reaches a consistent peak brightness, making them usable as standard distance markers across billions of light years. Both teams expected to find that gravity was slowing the expansion. Both teams found the opposite. The universe is not just expanding. It is expanding faster than it was before. Perlmutter's team was so surprised by the result that they spent months looking for errors before publishing. There were no errors. The 2 teams published within months of each other in 1998 and 1999. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for the discovery. What they found a name for, dark energy, the label applied to whatever is driving the acceleration, remains physically uncharacterized. We know its effect precisely. We have no physical description of what it is. It constitutes roughly 68% of the total energy content of the universe by the best current accounting. And we do not know what it is. This means that when you look at the night sky, you are looking at a phenomenon embedded in a universe whose dominant component, the thing making up more than 2/3 of all the energy that exists, is unknown. Heinrich Olbers asked in 1823 why the night sky is dark. It seems like a simple question. If the universe is infinite and uniformly filled with stars, then in every direction you look, Your line of sight should eventually terminate on the surface of a star. The entire sky should be as bright as the surface of the sun. It isn't. The question of why it isn't became known as Olber's paradox, though the problem had been noticed by earlier thinkers. Kepler mentioned it. Thomas Digges wrote about it in the 1580s. Olbers proposed that the darkness was due to absorbing material in space-blocking distant starlight. He was wrong about the mechanism. The correct answer was worked out more rigorously in the 20th century, and it has two components. First, the universe is not infinitely old. It has been in its current form for roughly 13.8 billion years, which means there has been a finite amount of time for starlight to travel. The light from stars beyond a certain distance has not reached us yet. Second, the universe is expanding, which means the light from distant stars is redshifted. Its energy is stretched into longer wavelengths, dimming it below the visible threshold. The darkness of the night sky between the stars is not emptiness. It is the places where the light hasn't arrived yet. The dark patches are not absences. They are delays. Every black gap in the night sky represents light that is in transit, coming from stars and galaxies that exist, whose photons are moving toward you right now and will reach you or your planet in 1 billion years or 10 billion, when the sun itself may no longer be burning. Stand outside on a clear night. Look up. The photons arriving at your eye left their sources at different moments, ranging from a few years ago to several thousand years ago. They have been traveling at the maximum speed that information can travel in this universe. They have crossed distances that no object with mass can cross. They carry information that is already old, some of it ancient by any standard that touches a human life. And they arrive simultaneously, registering in your retina as a single image that your brain assembles into the perception of a present-tense sky. The sky above you is not a view of now. It is a composite of the past, hundreds of different pasts arriving simultaneously, organized into a picture that looks immediate. Every point of light is a signal from a different historical moment. The sky is not a window. It is an archive, and the archive is incomplete. Parts of it will never arrive. Parts of it have not been sent yet. Parts of it were sent from sources that no longer exist, and the news of their ending is in transit. The night sky isn't a view. It's a record, and no one living will ever read all of it.